Okay, this is indefinite integrals continued. And notice I've dropped antiderivatives. It's true that indefinite integrals or even integration we use interchangeably with antidifferentiation. So we normally aren't going to say antidifferentiation or antiderivative. We're just going to say integral. So remember we looked at Rule 1 and 2, and not they're in any particular order. Rule 3 of finding integrals was what happens when we have the integral of a constant times a function with respect to x. And what the rule said is we can factor that constant outside the integration symbol and concentrate only on finding the integral of the function. Okay, that's what the rule says. And, you know, we're kind of hard-pressed here to even have any idea of how that might work. And so let's start out with something that we did kind of in the beginning. And if you recall, our very first problem before we even saw these symbols was we asked for the antiderivative of 5x to the fourth. I believe that's what we did, okay, if you look way back. And so here's the way we're thinking of this. Let me come over here. See, we're comparing k times f of x with what we have, which is 5 times x to the fourth. And so it's this 5 that's the constant, and this x to the fourth we can think of as the function. So it's really kind of making it very elementary here. So according to this rule, what we can do is we can move that 5 to the outside of the integral, and then we have 5 times the integral of x to the fourth power. And of course, that we have a rule for, don't we? See, we know how to find the integral of x to the fourth power. That's our power rule. So we'll write down this 5 that's in front, and now we're finding this integral of x to the fourth. And remember how we'll do that is we'll add 1 to that exponent. See, that 5 there is the n plus 1. That's the old exponent plus 1. Excuse me, the old exponent, which is 4 plus 1. So that's where that 5 came from. And then remember, in front of that, we have to put the reciprocal of that new exponent. And so the reciprocal of 5 is 1/5. And then we don't forget to put our plus constant of integration. And now we look at this to simplify, and we know 5 times 1/5 is just 1, and so this becomes x to the 5th plus our constant of integration. Now, we figured that out earlier without this rule. But now, with this rule, we figured it out kind of another way, and this rule, this constant, the integral of the constant times the function rule, is going to help us in situations where we might not otherwise imagine it. So, and here's what I mean. This next example, we'll use the same number 5, but what if it was the integral of 5x to the second, say? Then we have kind of a different scenario. It's hard for us to imagine what function we can take the derivative of and get 5x to the second. So this constant times a function rule, we're going to think the same way. We're going to think of that 5 as the k and that x squared as the f of x. So when we think in those terms, then we end up with, bring that 5 outside times the integral of just x squared with respect to x. And then, as before, we know how to integrate x squared, don't we? We'll increase the exponent by 1, so that will give us an exponent of 3. But in front of that, we have to offset that new exponent by the reciprocal. So we'll have the reciprocal of 1/3, of 3 there, which is 1/3. And then don't forget our constant of integration. And now when we simplify, we have 5 times 1/3, which is 5/3, times x to the power 3 plus our constant of integration. So that's our answer. Now, if we were checking, and I'm not going to do this many more times, but I'll do it later. But if we were checking, what we want to know is when we take the derivative of our answer, do we get our original integrand? That is, does that give us 5x squared? Well, when we take derivatives, remember, and we have a sum, that's the derivative of each term, isn't it? So we take the derivative of the first term plus the derivative of the second term. Now, when we take the derivative of 5/3 times x cubed, we think of multiplying the 5/3 when we bring down the exponent 3, and we decrease the exponent by 1, so we get an exponent of 2. And then when we take the derivative of a constant, it doesn't matter what constant, we get a 0. And then we look here and say, well, 5/3 times 3 is 5, and we have that x squared, and of course plus 0 doesn't change that. And so that is in fact the integrand, and so we know that we have the correct answer because the derivative of it is our original starting position. Now, let's look at another example, just so that we see a variety. And here's what I mean by that. What if we had the integral of, suppose it was 3t to the 7th power divided by 2. Let's just use that. Now, because the variable's t, then we would have a dt there instead of a dx. Now, there's a lot of confusion going on here, and I'm going to come back and address some of these things a little later again. But to be direct about this, we need to think of this as, can we think of this as a number times t to a power? And so what I'm looking at here is I'm thinking, well, this is the same thing as 3/2 times just t to the 7th power, isn't it? And then I can think of that, oh, well, there is my k value, and there is my, in this case, my f of t, not f of x. So I can bring that 3/2 to the outside, and I just have to worry about integrating t to the 7th power here. And so I remember how to do that with the power rule. I increase the power by 1, so I get a power of 8. But in front of that, I have to have the reciprocal of that new power. I have to have a 1/8. And then don't forget my constant integration. And remember, I'm doing this in t's and not x's. And then I look at the fraction 3/2 times 1/8. And what is that, 3/16? So I get 3/16 times t to the 8th power plus my constant integration. And that would be my answer. And we could check it as we did previously. That kind of gives you an idea that sometimes we have to manipulate before we're ready to find the integral. Now, that kind of, well, I guess that doesn't set us up directly. What I really want to do now is, I guess, look at the fourth rule that I mentioned in the beginning. After we complete some examples here, it's going to open up a wide range of things we can find the integrals of, or the antiderivatives of. So this fourth rule says, if we have the integral of a sum of functions or of a difference, that is, if we have a plus or a minus in between, that we can really think of that as finding two different integrals, and then adding or subtracting appropriately. So here again, we can't even imagine how this might fit together, except this is what allows us to deal with finding integrals, say, of polynomials. Say, for instance, what if we had the integral of 3x squared minus 2x to the 5th? Now, when I say that, then maybe you can imagine, oh, well, this is like the f of x, isn't it? And this is like the g of x. So this rule allows us not to think about what function I can take the derivative of to get 3x squared minus 2x to the 5th. It allows me to break it down into two simple problems. That is, all we need to worry about is what's the integral of 3x squared with respect to x, and then subtract whatever the integral of 2x to the 5th with respect to x is. And so we get to think about little problems instead of one big problem. Well, previous to this, we saw that if we have a constant times a function, that we can take that constant outside the integral sign. So we can write this as 3 times the integral of x squared with respect to x. And then over here in this second integral, we can do a similar thing because the constant is 2, isn't it? So we can factor that outside, put that outside the integral sign, and now we just have to worry about what's the integral of x squared and what's the integral of x to the 5th. Okay, well, when we look at the integral of x squared, we remember, how do we do that? We have to increase the exponent by 1, don't we? So the new exponent is 3. And then in front of that, we have to have the reciprocal of that new exponent. Now, over here, we've got minus, and we've got this 2. When we integrate x to the 5th, we increase the exponent by 1, but in front, we have to put the reciprocal of that new exponent. Okay, and then, of course, we don't forget our constant of integration. Well, now we just go back and simplify. And 3 times 1/3 is just 1, so this is x to the 3rd. And then we have a minus sign, and then we can figure out that, look, 2 times 1/6, 2 over 6 is the same thing as 1/3, isn't it? So that becomes 1/3 times x to the 6 plus our constant of integration. So although it was a relatively complicated function, we broke it down into a couple of simple pieces. And so remember, let me remind you again, pardon me, the way we would check to see whether we've done this right is we would take the derivative of our answer. And for us to be right, we expect that derivative to give us our original integrand. We would expect to get 3x squared minus 2x to the 5th. And I'll just leave it to you to check that, but I'm sure that when you do check it, you're going to find out that that's what we do get. Okay, I'll just leave that to you. Now let me make one other point here before we leave this particular example. We'll look at some more. And the point that I want to make is, well, actually maybe a couple of points, but the point that I want to make is you may have this question, because remember what we did is when we found it, I want to kind of go back to this step right here, okay, for just a moment, and explain to you something that happened that I kind of hid from you. So this is the step we're at. Now, when we look at this integral, okay, we end up with, what do? We have an x cubed, and we have to put a 1/3 in front of it, but now this is an integral, and so we have an integral, a constant of integration. And see, I've got 2 different integrals, and so I'm going to have 2 different constants of integration, aren't I? So let's just call this one c subscript 1 for right now. And then over here, I'm going to have minus 2 times, now when I do the integral here, what am I going to have? I'm going to have an x to the 6th and a 1/6 in front of that. But remember, I have to have this constant of integration that goes with this integral. So that's a different constant of integration. Now, when we end up kind of letting the dust settle, and there's still things in here to be an issue, but when we let the dust settle, I've got this x cubed, and I have this minus 1/3 x to the 6th, and I've got 2 different constants of integration here. But what we do is we call these arbitrary constants. We're not naming what constants they are. I mean, we don't know what constant this is. Any constant there would be appropriate, and any constant there would be appropriate. So what we really do is we ignore, just as I did, the separate constants, and we combine them all into one. And so we don't do that on each separate step. We just wait until the last step, and it's like we're combining all those constants, and there is our constant of integration. So if you had a question about that earlier, that's the reason I approached it the way I did. Okay, let's look at this example now. You can see it's red. Find the integral and it's the integral of 3x to the fourth minus 7x cubed plus 5x minus 10 with respect to x. Now, the rules we have, let's talk about the way this is done in theory, and then the way we do it in practice. So, by using the rules formally, so using the rules formally. Well, the first thing that we have here is a sum and difference of a bunch of different terms, and so we would use the rule about when we have the integral of things added and subtracted together, that we can break that into several integrals. And so we would think, well, we have the integral of 3x to the fourth with respect to x. Then we have minus the integral of 7x cubed with respect to x. Notice I'm putting that dx each time because it goes with an integral. Plus the integral of 5x with respect to x. And then finally minus the integral of 10 with respect to x. So that would be formally the first step we would take. Now the second step we could take is when we look at the integral, the very first integral, we have a constant 3 times x to the fourth. And so the rule that's a constant times a function tells us that we can factor that constant 3 out, take it outside the integral sign, and so then we just have 3 times the integral of x to the fourth. And of course, the purpose of doing that is we know how to use the power rule to find this integral of x to the fourth. And then we have minus the integral of, we have a 7 times x cubed, so that 7 we can bring in front of the integral sign, can't we? And so we just have 7 times the integral of x to the third power. And then when we look at the next integral, we have a 5 times x, so that constant 5 can be factored out or taken in front of the integral sign, and so we just have the integral of x with respect to x. And then, of course, we have the integral of 10. I suppose we could factor that out, but there's really no other factor there, is there? And then we can do each one of these integrals separately. And, I'm going to stop after this first one, but here's what we're thinking. Well, maybe I'll do a couple of them. We know how to integrate. We have 3 times the result of this integral, and we know how to integrate when we're dealing with a power of x. We would increase the power by 1, so we'd get a power of 5, and then we'd have to have a factor in front of that that's the reciprocal of that new power. And then similarly here, we have the 7, but we're going to multiply with the integral of x cubed. And of course, we know how to integrate x to a power. We increase the power by 1, so now it becomes the fourth power. But in front of that, we have to put a factor of 1/4. That's the reciprocal of that power. And then we would continue doing this, blah, blah, blah there. We would go on. Now, that's what we would do formally. But in practice, this is the way I do it, okay? In practice, I think out the steps, necessarily writing the steps. Let me rewrite the entire problem first, okay? Let me rewrite the entire problem here, that we have the integral of 3x to the fourth power minus 7x to the third power plus 5x minus 10. And we're integrating with respect to x. Now I'm going to come underneath just so I can compare. Here's the way I think about this problem. I know I can break it up into 4 different integrals, but I'm going to just imagine, well, what if I'm just thinking about the first integral I would have? I really am just integrating that term. And since I have that constant 3 in front, I know that that's going to hang around just like I saw above. And so now I'm thinking, well, how do I just integrate x to the fourth? Well, of course, I know how to integrate x to the fourth. I increase the exponent by 1, so I have a power of 5. And in front of that, I have to put the coefficient, which is the reciprocal of that new exponent, so a 1/5. And then I move on to the next term, but of course I notice the sign right here, and I know that's going to be the sign that I have down here. So I've got that minus sign, and that constant 7 factor I know is going to be there. So I go ahead and write it down, and I'm getting ready to multiply it with just the integral of the x cubed. And so now I'm just thinking, how do I integrate x cubed? Well, I increase the power by 1, so I have a power of 4, and in front I have to put the factor that's the reciprocal of that new exponent. So that's a 1/4. And then I write down my plus sign that's here, okay? And I see the 5 that's there, and so I know I'm going to have that 5, and I'm going to multiply it with the integral of x. Now that kind of lesson, let's go down to the bottom of the page here, because we really haven't talked about the integral of just x, have we? And it's not really anything special, but if we haven't talked about it, it might catch us off guard. So let me remind you that x is really just x to the first power, see? So we really have the integral of x to the power. And how do we integrate x to the power? Well, what do? We increase the power by 1. So when we add 1 to 1, we get 2. And then we have a factor in front of that that is the reciprocal of that new exponent. So the integral of x is 1/2 x squared, isn't it? Now, of course, we recognize that we have plus a constant of integration if that was all there was to our problem, but we're in the middle of a problem up here, so I'm really going back up to the top, okay? So I'm back to integrating x. I've already written down my 5, and so I understand the exponent that is on x is 1, so when I increase that by 1, I get an exponent of 2. And then I have to put a factor that's the reciprocal of that new exponent in front. And then I see that minus 10. Well, now I'm thinking, see, I'm really thinking, I've got the minus sign, I'm really just integrating a 10 there, aren't I? That's the way I'm thinking about this. And I remember when I integrate a constant, it's just that constant times the variable that I'm integrating with respect to. And in this case, it's x. And then again, of course, if that was the only part of the problem, I'd say plus c. So anyway, I'm back to integrating the 10, and I know that that's a 10x. And, of course, at the very end, I'm going to put my constant of integration that's accounting for all of that. And so that's what it would look like after I went through one pass of doing the integration, rather than writing down all those separate steps. And then, of course, I end it by going back through and doing all the appropriate multiplications. Like 3 times 1/5, I would write as 3/5. And then I make sure my x doesn't look like it's in the denominator. That's times x to the 5th. That 3/5 is a coefficient, isn't it? And then the next term, I have 7 times 1/4, which is 7/4. And, of course, that's times x to the 4th power. And then I have 5 times 1/2, which is 5/2. And, of course, that's times x squared. And then I have just a minus 10x and a plus c. And so there I would have my integral completed. And we could check that by going and finding the derivative of each of those, and that's probably a good exercise. But for now, we'll just call that good. There are we have the 4 rules that we've talked about already. And we have 2 special integrals that I want you to be aware of. And we won't use them a whole lot yet, but we will use them in the future quite a bit. And the first one is the integral of e to the x with respect to x. Now remember, when we get an answer, when we get the result of this integration, the result's called an antiderivative, or we just say the integral of. But the derivative of our answer has to give us what we were integrating. And if you recall, when we find the derivative of e to the x, we in fact get e to the x, don't we? So we can just remember from past ideas that the integral of e to the x will in fact just be e to the x. Because the derivative of this side, see, when we take the derivative of this side, we're going to just get e to the x, aren't we? So that's how we can comfortably say that the integral of e to the x with respect to x is e to the x plus a constant of integration. So that's the first special integral I want you to know about. And the second one is related to this idea. I'm going to write it down in a moment. Well, let me tell you this. It's the integral of 1 over x. See, that, which is the same, by the way, as the integral of x to the power -1. See, we've already talked about that we can't use the power rule on x to the -1 power, because that would give us a 1 over 0, wouldn't it, when we calculated the reciprocal of the new exponent. And so we haven't had a way of doing that. And let's just recognize x to the -1 and 1 over x are the same. And so what we need to know is how we integrate 1 over x. Now this is related to, okay, let me come down here. It's related to, there's a little issue you'll just, I hope, will accept from me, but it's related to finding the derivative of the natural log of x. And we know that when we find the derivative of the natural log of x, we get 1 over x, don't we? And so if you would accept from me, it's reasonable that we would get the natural log of x as our result here, right? Because the derivative of natural log of x is 1 over x. Now here's the only catch to this. Remember that we can't take the natural log of negative numbers. And so we've got to make sure that when we have our answer here, we don't have the answer that's the natural log of a negative value, that x can't be negative, or we can ensure that by making sure that we have a positive result there. And the reason that absolute value has to be there is because 1 over x doesn't have the restriction that x can't be negative, but the natural log of x does. And so since we can't restrict x as 1 over x, we'll make sure we're just taking the natural log of a positive value by saying absolute value of x. So these are the two special integrals that we just have to memorize. Now, just real quickly, and real quickly is all we're doing here, a couple of examples. We might be asked to find the integral that would be, let's say, 5 times e to the power x with respect to x. And if we were asked to do that, what we would do is we'd notice that factor of 5 in front of the e, and so we could factor that 5 out. And so once we factor that 5 out, we just have the integral of e to the x with respect to x. And then we can use the above special integral and say, look, here's our 5, and when we integrate e to the x, we just get e to the x plus our constant of integration. And so our final result here, we would write as 5 times e to the x plus our constant of integration. Now, you know, to carry this a bit further, let's do another example. And I'm going to change this one just a bit. I'm going to change it quite a bit. Suppose we're asked to find the integral of e to the x over 2. I tell you what, I apologize to you for this, but let me say the integral of e to the t over 2. Now, our variable is t, so down here, instead of saying dx, it has to say dt. So that's the integral we're asked to find. Okay, well, the first thing that we have to do is make sure that we can use rules or special integrals that we already have. And we don't have a rule about e to t divided by 2. But what we can do, and we have to be vigilant about this, that we have to be on the lookout. We can write e to the t over 2 as, so let me rewrite my integral sign because I haven't done anything with that yet, but we can write e to the t over 2 as 1/2 times e to the t over 1, or just 1/2 times e to the t. And then we recognize that this is really just a constant times e to the t. And so similar to the problem before, we can take that 1/2, factor it to the outside of the integral sign, and then we just have the integral of e to the t with respect to t. Now, of course, here our variable is t, so our answer wouldn't be e to the x, it would be e to the t. So we would have our 1/2 times e to the t power plus our constant of integration, and that would be our result here. And we could write that as e to the t over 2 again if we wanted to. Okay, our last example has to do with this 1 over x business. So for instance, suppose we were asked to find the integral, let's say, of 3 times x to the negative 1 power with respect to x. Well, as we begin to work on that, we see that we can, well, let me rewrite the problem down here. Okay, so we're asked to find this integral. Well, we recognize we've got a constant factor of 3, so that can be factored out to the outside of the integral, can't it? And so then it's just the integral of x to the negative 1 with respect to x. Now, we can think of that as 1 over x, or we can say, oh, yes, there's a special rule for this. And so we have our 3 factor in front, and we're multiplying with the result of the integral of x to the negative 1, which is just the natural log of the absolute value of x, isn't it? Okay, plus our constant of integration. And so in this case, our final result, or our answer, would be right here. Well, this ends the part 2 of antiderivatives or indefinite integrals. But what we are going to do in part 3 is I'm going to first review the rules that we've got, and then give you some warnings about rules that we don't have, that sometimes students make a mistake of making up a rule. And then after that, we'll go through several more examples that mixes all of these rules together.